Good afternoon, everyone. Hope you are doing well. So, quickly, let's have a small recap before our today's class and then discuss our new topic for today. Okay. So, if you remember what did we discuss in the last class, try to remember and take a note of it once with your on your own conscious. Okay. I think try to remember, right? So, what we discussed about a few concepts about chemical equilibrium and what is exactly equilibrium. We have discussed much about it, right? So, and we also seen that where we can see the equilibrium state actually first. So, based on that, we have seen two types of reactions, that is reversible and irreversible reaction. In reversible reaction, we'll not be seeing equilibrium state, right? We'll be seeing equilibrium state, no, we'll not be seeing equilibrium. But in irreversible case, we'll be seeing the equilibrium condition where the rate of formation of products, let's say RF, will be equal to rate of decomposition of products into reactants in this way. Let's say rate of forward reaction is equal to rate of backward reaction. That is way more easy, right, to remember. I think what how many reactants are converting to products will be equal to the rate how much the product is converting into reactants. But we cannot say the exact concentration of reactant and exact concentration of product will be equal. Okay, we'll not be saying exactly they'll be 50 all the times. So it may change depending on what type of reaction we are talking. Okay. After seeing where equilibrium is possible, we have seen what types of equilibriums are there. One is a physical equilibrium, nothing but can see oil and water, let's say oil and water. If you take this in a beaker, what happens? Which one is having a more density will be going down below the layer, and oil will be above the layer because its density is less compared to water. This is a physical equilibrium example, right? No, immediately after you are mixing it, will it separate it instantly? No, it will take some time to separate. Right? It will come to an equilibrium at last. No, and chemical equilibrium, which we see in reactions, thermal equilibrium. If let's say we are keeping a hot object, the red object, and a blue object, that is cold object. What happens after a certain time? The temperatures will be equal. After some time, the temperature transfers will happen, and they'll have equilibrium temperature. This was a thermal equilibrium. Now, what was a mechanical equilibrium? You have seen the balance, right? Mechanical equilibrium, where I kept a stone here and four stones here and a single stone like this, right? So this is also a mechanical equilibrium. We have seen such kind of types of equilibriums, right? After seeing this equilibrium, we have seen on what conditions this chemical equilibrium does depend. If you change the concentration of reactants, or if you change the concentration of products, or if we change the temperature of the reaction itself, will the equilibrium change? This is what we observed these things, right? So we know that if you change the temperature, the equilibrium is also shifting, but it is not changing much depending on the concentration of the reactants or products here. Like what we are using, the initial number of moles, or what we are using. If we see 1 mole reaction or 2 moles reaction, after balancing, if we are increasing the number of moles in all the cases, product side and reactant side, the equilibrium doesn't shift much there. Let's see our today's concept, that is equilibrium constant itself. How do we write equilibrium constant and how we do some problems based on equilibrium constant? This will be seen today. Okay. And we'll be seeing reaction coefficient. And what is the use of equilibrium constant and reaction coefficient we'll be seeing at last. So let's see our first thing, that is equilibrium constant. Now, what is equilibrium constant and where we can see? You know that we can see this only in a reversible reaction, right? So directly we are going to a reversible reaction. We are not talking about irreversible reactions here. So whenever rate of reaction is directly proportional to active mass of reactants. Okay, remember the word active mass. We are not talking about mass of the reactants. How much moles of reactant we are using. We are seeing how many are actively participating in the reaction, how many moles of the compound. Let's say you are taking 10 moles of the compound, but actively only 5 moles is reacting. So we will be seeing the rate based on that available 5 moles only, not all the 10 moles of the reactant. Okay. That is nothing but active mass. What is actually involved in the reaction? Okay. So you have 10 fighters, only 5 fighters are able to fight, other 5 are not able. So you do your calculations how you win based on these 5 itself, right? You'll not care about the other 5 because they cannot fight. So the same thing here. We'll be seeing what are the reactants which are available to reaction and which can improve the rate of the reaction or decrease the rate of reaction based on them. Okay. Now, if you see, if you want to write the rate of forward reaction here, how do you write? Nothing but a rate of forward reaction is equal to forward constant, or we can say rate of forward reaction is directly proportional to concentration of the reactants, right? How many reactant is available actively participate in the reaction. Now, if you remove the proportionality, what will be? You'll get a constant that is equal to forward reaction constant into concentration of R. So this is what we write. The same case we can write for backward reaction also, right? Nothing but that is equal to Kb into concentration of product. Okay. No. Firstly, before writing all these rate of forward reaction, rate of backward reaction, you are going to see much about the active mass itself. What is active mass means nothing but whatever the substance which is involved in the reaction, okay, which is actively participating in the reaction so that it can give products. Now, how much is involved? That is only giving the rate of the reaction. Okay. Now, if you see it in that way, if we take liquids as our reactants, then what do we see? How do we see the active mass, or how do we see the active molecules which are participating in the reaction? That will be seeing using molar concentration. That is generally molarity of the compound will be seen. Okay. Concentration is nothing but number of moles per volume. Okay. N by V terms will be seen. Okay. How much moles of the compound is available in the V ml of the solution or V liters of the solution you are taking. So here generally as per molarity, we will be taking liters per liter of the solution. So in that case, number of moles per liter. So how many moles of the actively participating reactant are available in the liter of solution? This is our main concept. Okay. Nothing but kind of like density. How many moles are present in a particular per centimeter cube or meter cube in that? Okay, clear. Like a density itself. Okay. So in a homogeneous solution, if you see, molar concentration will be same everywhere, right? It doesn't change because we are taking homogeneous solutions. Nothing but density of the ions will not change. Wherever in the solution you see, the density will be same. Clear. Now, another thing, if we take gases, then how would we see? How do we see? So in questions, sometimes they may give you partial pressures or pressures of the gases. So you take pressures at that time. If they give you again moles or volume of the gas, then you can take N by V here also. In gases, in case of gases, you can take N by V, nothing but molarity concentration terms, or in gases, if they mention partial pressure, you can take partial pressure of the gas itself. Anything is fine. But in solutions, they'll be giving concentrations and volumes itself. And in case of gases, they may give you moles and volume. At that time, you can take concentration as active mass, or if partial pressure given, then you can take partial pressure as the active mass. Nothing but partial pressure of the gas is nothing but how much collisions are there due to the gas molecules on the surface of the container, let's say. That means as the collisions increase, the probability of the reaction will increase, yes or no? So that is solely depending on pressure of the gas. So that is why we are taking pressure of the gas as active mass here. Now, next thing, pure solid. So in pure solid, we'll be taking as active mass as 1. Why? So I said, remember one thing, density, right? Nothing but if you see concentration of the metal ion or any solid ion in the solid itself, if you see at any particular side, at any particular corner or anywhere in or in center of the crystal itself, everywhere you see the ions will be same. That doesn't change. The density doesn't change, right? The density is same everywhere, or the concentration of the ions anywhere in the whole metal or whole solid ion is same. It doesn't change. So that is the only reason why we'll be taking active mass as of pure solids as 1, as well as active mass of pure liquids as 1, due to their concentration being constant at all parts of the volume of the solid or liquid. That is the only reason why we are taking active mass as one. So are you clear with active mass? What is active mass? Nothing but which is actively participating in the reaction. That is active mass. Here we'll be seeing mainly on the based on the concept of concentration or density. If you have any doubts, try to text in the chat. Okay, if you don't have any doubts, let's move to the next concept then. Let's see how to write equilibrium constant. So before writing equilibrium constant, we need to know what is a forward reaction and how we do the forward reaction rate. Now let's say we have a R is in equilibrium with P, that is reactant is in equilibrium with product, right? If that's the case, then now rate of forward reaction, how do we write? Nothing but we have already seen that rate of forward reaction. Now, how much product is being produced is directly dependent on the reactant concentration itself, right? If you take 1 molar of reactant and 2 molar of reactant, 2 molar of reactant, both have different amounts of reactant availability. So they'll be reacting differently in each cases. So as we increase the number of moles available for the reaction, the product production will increase. Yes or no? Right? The same thing. Now, here the rate is directly dependent on the concentration of the reactant. As we increase the availability of active reactant, the rate of the reaction will increase. So if you remove the proportionality constant, what we'll be writing? Rf is equal to forward rate constant into rate of the concentration of the reactant. This is our formula for forward reaction. Now, the same case in case of backward reaction also, where we'll be writing Rb is equal to Kb into concentration of product. Now, how much product can convert into reactant? Nothing but how much product is available, right? How much product is available? That is nothing but concentration of the product itself, right? The same thing. We are writing it exactly opposite. Try to note down. First thing, whenever you are taking equilibrium constant, forward reaction depends on the reactant concentration, and the backward reaction depends on the product concentration. Clear? No. How to find out equilibrium constant? What is equilibrium? Nothing but whenever the product reactants are converting into products and product is converting into reactants. Now, in this case, what we talked at equilibrium, what we talked, rate of forward reaction is equal to rate of backward reaction. Yes or no? We have seen this, right? So based on that, we'll be writing the equilibrium constant value. Let's see how to write it. No, nothing but rate of forward reaction is equal to rate of backward reaction, where Kf into R, I'm just substituting the Rf values and Rb values. Rate of forward reaction is equal to rate of backward reaction. No, Kb into concentration of product. If we just rearrange the formula once again, Kf by Kb is equal to concentration of product by concentration of reactant. Now, if we are dividing both constants, we'll get a new constant that is nothing but equilibrium constant. That we'll call it as equilibrium constant, nothing but concentration of products by concentration of reactants. Are you clear how to write equilibrium constant? Nothing but what you need to do, just divide rate of forward reaction by rate of backward reaction. That will give you the equilibrium constant value. No. Before going to the problems of equilibrium constant, we need to understand some terms, how to write the active mass and how to write it actually in the equilibrium constant itself. What is the dependency on the number of moles of the gas, or what is the pressure of the gas? How to mention these in equilibrium constant values. So first we'll be seeing this, and then we'll be going to the main problems again. According to law of mass action, what we'll be seeing for a reversible reaction at equilibrium and at constant temperature. Why we are taking constant temperature? If we are changing temperature, that means we are changing the rate of the reaction. Why? Because if we change temperature, kinetic energy of the molecules increase, right? So if energy of the molecule is increasing, the reactions may be favored or the reactions may be unfavored. This may happen. So that's the only reason why I'll be taking it as constant temperature. Okay. And certain ratio of products and reactant concentration have a constant equilibrium constant. Clear, right? What did we discussed yesterday? Where it doesn't depend on the what type of elements we are taking or anything. If we are taking a single reaction in the balanced reaction, if you are doubling it also, the equilibrium state will be same itself. Equilibrium state doesn't change. Okay. Now let's see how to write the values. Now, if this is our equilibrium reaction where A, B, C, D, a, small b, small c, and small d are our stoichiometric values. Okay. Stoichiometric values. Okay. Nothing but number of moles. If these are the number of moles and A, B, capital B, capital C, and capital D are our molecules itself, reactants and products. Okay. If these are our reactants and products. If that's the case, then how to write equilibrium constant in these cases? Until now, we didn't see the importance of number of moles in equilibrium constant, right? So let's see what is happening in this case. If you write the equilibrium constant, nothing but concentration of products by concentration of reactants, right? Where K equilibrium is equal to concentration of products, that is concentration of C, power stoichiometry value, that is C, into concentration of D, power stoichiometry value, that is D, by reactants, that is concentration of A power A into concentration of B power B. Clear. This is how we write equilibrium constant values. Nothing but rate of forward reaction by rate of backward reaction. Again, same thing, same concept. Rate of forward reaction is nothing but Kf into concentration of A power A into concentration of B power B. This we learned in the kinetics, right? Rate is directly proportional to rate of forward reaction is directly proportional to rate of concentration of reactants, and rate of backward reaction is proportional to, if it is possible, then only rate of backward reaction is possible, then only we'll be writing rate of backward reaction is proportional to concentration of products. Now, if we do that, we'll be writing the law of chemical equilibrium values and we'll get a K equilibrium, ultimate equilibrium constant itself. We can represent a K equilibrium or Kc also, both are same, they're not different. Okay. Are you clear with this concept? How to write equilibrium constant? No. If you don't have any doubts, let's move to the next section. Firstly, Kc is a constant, and I said right, K equilibrium is also denoted as Kc. Both are same. Okay. Now, Kc and is a constant and is called equilibrium constant in terms of concentration. Okay. In equilibrium constant expression, all concentrations are at equilibrium and are expressed in terms of moles per liter. It is all these concentrations we know we are talking about N by V values, right? Nothing but mole per liter values only will be taking, not the others. So this is how, if the units are different, how to calculate the units directly using the formula is mole per liter is everything same, but whatever power we are using here will be changing. What is the stoichiometry value? Just write a power to it. That's simple. You'll get the units of Kc. Generally, they may ask you units of Kc by giving a reaction. So what you need to do, just write down mole per liter and raise the power to its stoichiometry values too. If it is products and reactants. Simple. Now, let's write equilibrium constant for a reaction and how to write it. So, initially, what will the reaction contain of? Only reactants, right? Whenever you are initial, let's just now you added ethyl alcohol and acetic acid. Then at that particular instance, what are present? Ethyl alcohol and acetic acid itself, right? So, after some time, the reaction starts and it will be converted into esters. Now, if that's the case, whenever we take initial conditions when time is equal to 0, it didn't start, the reaction didn't start yet. At that time, the concentration of C2H5OH, ethyl alcohol, will take it as 1 and acetic acid take it as 1. Now, what is the concentration of products at this particular state when the reaction actually didn't start? Can you answer in the chat? Yeah, the concentration of the products is 0, right? at initial state, whenever the reaction didn't start yet. So now afterwards, let's say whenever the reaction is attaining equilibrium state, let's say whenever equilibrium state, whenever we are attaining equilibrium state after t is equal to 0, something t is equal to t, sometime after some time. Now, what will be the concentration? There will be certain amount of products formed at that particular state, right? Let's say that concentration is X and same concentration of H2 also will be formed, right? Both concentrations will be same, product concentration. Now, how much concentration of CH3COOH acetic acid is lost, or ethyl acetate, ethyl alcohol is lost is nothing but 1 minus X, right? How much product is formed? That much you need to remove. Simple, right? 1 minus X in both the case. Now, let's say the H2O formed is 2, then write the formation of product as 2x. Let's say ethyl alcohol we are using is 2, then like in the balanced equation, if it is 2, then write it as 1 minus 2x. Like how many moles are available, that much amount of moles will be reacting, right? So that is what we need to mention in the x values. Okay. Just for simple example, I'm writing. Okay. Let's say we are having 2 moles of acetic acid. Then what you need to write? 1 minus 2x. Simple. Clear? If you are having 2 moles of water, then write it as 2x. Simple, nothing more. Just if you are having seeing any moles in the balanced equation, only in the balanced equation, then just try to keep it to before x, nothing else. Simple one. Now, if we continue, again, just try to write the equilibrium constant here. How do you write equilibrium constant? Equilibrium constant, K equilibrium is equal to concentration of products, that is concentration of H2O, concentration of CH3, COO, C2H5 by concentration of C2H5OH, those are reactants, okay, by acetic acid, concentration of CH3COOH. Clear? Now, as there are no stoichiometric values, all have stoichiometric values as 1, so I'm not representing that, okay. If you write this elaborately, nothing but in terms of 1 minus x and x, if you write like that, let's say he has given V volume of solution. V volume of solution. Now, in this case, we are going to take the concentration as n by V values, right? Number of moles, how to write? Nothing but 1 by x by V, 1 minus x by V, x by V, and x by V, right? Just substitute these values. What you'll get? 1 my x by V, that is nothing but product concentration, into x by V by 1 minus x by V into 1 minus x by V. Simple, right? This is what we write in terms of equilibrium constant value. Okay. If you know denominator and the numerator both have equal number of volume terms, so you can directly cancel the volume terms and write it as x square by 1 minus x into 1 minus x. Do you have any doubts how to write the equilibrium constant in this case? Just try to find out the concentration, number of moles by volume term, and then substitute in the equilibrium constant. Nothing much. Okay, if you don't have any doubts, just try to write equilibrium constant for this case. The first one, I'll give you 2 minutes. Try to write it for 2 questions. Nothing but what you need to write? Concentration of products by concentration of reactants. So whenever gas is given, what you will be taking? Either concentration or either pressure of the gas. Any one you can take. Okay, you can try it. I'll be writing the answers. Okay, whenever gas is taken, either you can take concentrations, that is number of moles given by volume of the gas, or you can take pressure of the gas itself. Nothing but K equilibrium for PCl5 reaction, let's say K equilibrium or Kc is equal to concentration of concentration of PCl3 into concentration of Cl2 gas by concentration of PCl5, or you can also write as pressure of PCl3 into pressure of Cl2 gas by pressure of PCl5. Simple. Okay. One more thing you can write for NH3 ammonia. Now here if you see, The stoichiometry values came where K equilibrium is equal to concentration of N2, stoichiometry value is 1, so no issues. Concentration of H2, the stoichiometry value is 3, power 3. Concentration of H2 power 3, no. Concentration of NH3 ammonia power 2, the stoichiometry value is 2. If you write in terms of pressure, pressure of N2 gas into pressure of H2 gas power 3, same thing. We need to write in terms of pressure, nothing else. Pressure of NH3 gas, ammonia gas power, simple, right? How to write equilibrium constant, understood? Just write products by reactants. If it is solutions, only concentrations. If it is gases, you can write in terms of concentration or in terms of pressure. If you have a pure solid in the reaction, nothing but the concentration term or active mass is equal to 1. So they give you in the question itself that let's say ammonia is in liquid form and it is they are saying that ammonia is pure ammonia. Then you can take concentration of ammonia as 1. Okay. Whenever they mention in that particular sentence only. Now, if you write for this one, all are gases again, what you need to write? K equilibrium is equal to concentration of nitrogen oxide power 2 by concentration of N2 into concentration of O2. These brackets represents the concentration terms. Okay. Don't forget, whenever writing concentration terms for a molecule, try to mention the square brackets. Don't forget this. Now, if you write for this, as you can see, there are solids here, right? There are solids. First, write the equilibrium constant same way. Okay. And then substitute the solid values. Concentration of CaO, calcium oxide, into concentration of CO2 divided by concentration of calcium carbonate. Now, after writing the equilibrium constant, you can substitute the values if they are pure solids. Just remove what is the left out concentration of CO2. K equilibrium will be depending totally on concentration of CO2, not on concentration of calcium carbonate nor calcium oxide, as they are pure solids. Okay. Clear with this? How to write the Kc values? If you have any doubts, try to mention in the chat. Okay. If you don't have any doubts, now try to solve this problem. What is Kc for the following equilibrium when equilibrium concentration of each substance is given? Each substance is given. Simple, right? What is given? Reactants and products are given. First, write the reaction. How to write the reaction? You see here, nothing but SO2 is given, O2 is given, SO3 is given. You can either write where SO2 is reacting with O2 to gives rise to SO3, right? Now, we need to write both the reactions, right? Equilibrium constant. So, if you balance the reaction, sulfur is 1, oxygens are there. So, try to balance oxygens. You can write it as 2 SO3 and 2 SO2 so that the oxygens will be balanced, right? 4 oxygens, 6 oxygens on reactant side and 6 oxygens on product side. Now write the Kc value. Kc is equal to, or equilibrium constant is equal to concentration of SO3 power 2 by concentration of SO2 power 2 into concentration of O2. Simple, right? You can write it in this way. Okay. Now, all the concentration values are given. You can directly substitute and find out the Kc value. Try to complete that calculation. What you need to write? Nothing but SO3 value is 1.9 power 2 square, 1.9 whole square, and 0.6 whole square into 0.82 concentration of oxygen. Now the answer will be around 12.23 liter per mole. Don't forget the units, liter per mole. Why liter per mole? See, if you see in the previous case, what is happening? Whatever the units are there here, per square cancel, and the units are left are oxygens. Okay. That's why you're writing liter per mole, not mole per liter. Try to see the units. Units are important here. Are you clear with the units? If you have any doubts, try to mention in the chat. If not, I'll be repeating that once again. Units. Okay, I'll repeat. See, nothing but Kc. Sorry. Nothing but Kc what? Sorry. Kc is equal to SO3 power 2 by SO2, that is reactant power 2, into oxygen, concentration of oxygen. If you substitute, nothing but mole per liter whole square by mole per liter whole square into mole. Nothing but if you cancel both these, what is left? Nothing but liter per mole, right? Don't forget the units. Try to be good with the units. Now, try to do the another question. For the reaction, A plus 2B gives rise to, in equilibrium with 2 moles of C. He gave 1 mole of A is there, 1.4 mole, 1.5 mole of B is there, are taken in 2-liter vessel. At equilibrium, the concentration of C was found to be 0.35 mole per liter. Then equilibrium constant of the reaction would be. So what did I say? Whenever gases are given and moles and volumes are given, try to write the concentration term first before going to the calculation part. Now, if you see it in that way, where A plus 2B gives rise to is in equilibrium with 2C. All are gases and all concentrations are given. So let's follow that itself. You know, what is the initial moles of A and B? 1 and 1.5 moles at T is equal to 0. Clear? What is the initial concentration of C? 0. No. If you want to find it out at equilibrium state when T is equal to some time, we don't know. No. At that state, what is the concentration of C? You can write as 2x. Nothing but what they say. Keep it as x and what concentration of C and multiply it with the number of moles. Now, if you see the same thing, here what we'll be writing with for B, 1.5 minus 2x, and for A as 1.1 minus x. Clear? Just multiply the x, whatever the stoichiometry value for that particular term is there. If it is B for 2 is there, as for A only 1 is there, so I'm writing it as x itself. Okay. So how many moles are available? Those many moles will be react. That's the only point here. Now, if you write the volume term again, minus 1 by x, 1 minus x by volume, that is 2, right? 2 liters is given. That is 2 by 2 by. Now, we know that equilibrium concentration of C was found to be 0.35. That means what? 2x by 2 value is 3. 2x by 2 is equal to 3. If you see that, nothing but x is equal to, sorry, 0.35. 0.35. Clear, everyone? No. What is 2C value? Nothing but, no. Write the equilibrium constant K equilibrium is equal to concentration of C power 2 by concentration of B power 2 into concentration of A. Right? Now substitute the values. Just find out the values. You got the X value, right? Substitute the X value. You'll get the moles of each cases. As volume term is same every case, you can directly cancel out the volume term again. And then just find out the K equilibrium value. Okay. If you want to write, nothing but we'll be writing it as 2x is nothing but how much? 0.7 by 2 by, if you write 1 minus x, nothing but 0.35 minus 0.1, that gives us 0.75. 0.75 by 2 into again 2x, so 0.7 minus 1.5, you'll get a 8, right? So try to do this in this way itself, you'll get the answer as 2.36 liter per, you know, right? Again the units, why? Same thing, same like oxygen gas. You try to find out the units for this also. You'll end up with the answer as 2.36 liters per mole. Okay. If you have any doubts in the question, try to ask in the chat. Okay. If you don't have any doubts in the problems, then we'll go to next concept, that is characteristics of equilibrium constant. And how does it depend on different things, or will it actually depend on different things or not? We'll be seeing. First thing is equilibrium constant does not depend upon concentration of various reactants or presence of a catalyst or direction from which the equilibrium is reached. Now let's say you are doing a reaction, and initially 100 till 90% of the product is formed, and then the backward reaction started. So we'll not be seeing whether the reaction is going to 90% and then it is attaining the equilibrium, or directly initially whenever the 10% reaction started, automatically the backward reaction is also starting. So we'll not be seeing all those things. The equilibrium is the main part there. What is the final concentration of the product and final concentration of the reactant at equilibrium state is the main point. We'll not be seeing what is the initial thing, what is happening initially, what is happening after 2 minutes, what happening after 3 minutes. We'll be seeing immediately after adding the reaction or starting the reaction and at equilibrium state itself. Okay. Now, if you see the presence of catalyst, as we discussed yesterday, what does a catalyst do? Nothing but it will decrease the activation energy of the reaction. Nothing but it will decrease the energy required so that the reactants can be converted into products, as well as the products can be converted into reactants. So it is helping in both cases. The rate of forward reaction will increase as well as rate of backward reaction will increase, but it doesn't disturb the equilibrium state of the reaction. Clear? Don't forget this point. Okay. It is increasing how fast a reaction can happen, but it is not disturbing the concentration at equilibrium state. No. Upon concentration of various reactants also, whatever rate of forward reaction or rate of backward reaction is there, that will be constant on a whole. Okay. So the equilibrium constant is mainly affected by what? Temperature, or you can say stoichiometry values of the reactants and products. This will be showing the effect on reaction, both reactants as well as products. No. Equilibrium constant does not give any idea about time taken to attain the equilibrium. If I give you a Kc value, and can you say, like, if you are having Kc value of 2, that means it will take me around 2 minutes. So we cannot say that. We will be seeing the equilibrium value is only for what is the rate of forward reaction, what is the rate of backward reaction, and at this particular moment, what is the concentration of product, what is the concentration of reactant. This is the only terms we are concerned with equilibrium constant. We don't know how much time it will take to attain the equilibrium state itself. It doesn't give any information regarding the time. Next, equilibrium constant is dependent only on the temperature. Why? I said right, as we increase the temperature, what happens? As the kinetic energy of the molecules increase, so that may favor any one of the rate. That is, it may favor rate of forward reaction, or it may favor the rate of backward reaction. Any one will be favored. That means it is disturbing the equilibrium state. It is disturbing the rate of formation of reaction products and rate of formation of reactants. Backward reaction rate as well as forward reaction rate is affecting differently. It is not acting samely, or it is not acting in the same way as in case of catalyst case, right? What did catalyst do? It helped the forward reaction as well as backward reaction in same time. But whenever we are increasing temperature, let's say in case of exothermic reaction, what happens? In case of exothermic reaction, if you increase the temperature, what happens? The rate of backward reaction will be favored rather than rate of forward reaction here. And if we take endothermic reactions, if we increase the temperature, rate of forward reaction will be favored and rate of backward reaction will be unfavored. Right? So in this way, the rate of forward and backward reaction will be affected differently in case of temperature, but they will be affected same way in case of catalyst. Okay. Try to remember this point. Don't forget this. Now, when we come to characteristics of equilibrium constant. Before this, are you clear with this point? How it is dependent on temperature? If you're not clear, try to mention in the chat. Try to mention in the chat if you are not clear how the reaction equilibrium constant is dependent on temperature. Okay, if you are clear, that's no issue then. Let's go. The only reason why temperature is changing the equilibrium constant is as it is affecting rate of forward reaction differently as well as rate of backward reaction differently. It is not affecting both of them in the same manner. Now, if you see, first thing, characteristic of equilibrium constant and how it depends on stoichiometry value of the reaction. How it depends on stoichiometry value. We seen temperature till now. Now we'll be seeing stoichiometry value, how the equilibrium constant will change based on stoichiometry value of the reactants as well as products. That is a balanced equation. Now, if two chemical reactions at equilibrium having equilibrium constant K1 and K2, that means we are taking two conditions here where we are taking two different reactions where A is in equilibrium with, let's say, C, and B is in equilibrium with, let's say, D. Okay. The equilibrium constant for the first reaction is taken as K1 and the second reaction is taken as K2. Now, what is saying is that we are adding these two reactions. Okay. Nothing but we are adding these two reactions. How we are writing? A plus B is in equilibrium with products, that is C plus. So this new equilibrium constant is taken as K, capital K. Now, how we can relate the individual equilibrium states with the whole compound reaction state? He is asking that one. So if you see, what is the rate of reaction here? Nothing but equilibrium constant here, in this case, K1, let's say. So K1 is equal to concentration of C by concentration of A, right? Simple. Now write the same thing for K, BD reaction, where B is in equilibrium with D. K2 is equal to concentration of D by concentration of B. Simple, right? Now write the K value also. Rate equilibrium constant K is equal to concentration of products, that is concentration of C into concentration of D by concentration of A into concentration of B. Simple, right? Now, you know concentration of C by A is what? K1. Just substitute those values where K is equal to K1 into K2, where C by A is K1 and D by B is K2. Concentration of D by concentration of D. Now, how we can write whenever we are adding a reactions, what you need to do, just multiply the rate constants of individual reactions. Note the point. Whenever you're adding two different reactions with two different rate constants or equilibrium constant, two different equilibrium constants, then what you need to do, just directly multiply the equilibrium constants of both individual reactions so that you'll get the total equilibrium constant of the combined equation. Clear with this? Okay. Let's move to next one. Now, equilibrium constant depends on stoichiometry of the reaction also. Okay. Now, second case is if chemical reaction have equilibrium constant Kc, already saying Kc is the equilibrium constant. Now we are reversing the reaction. Then what is the new equilibrium constant? He's saying that you are taking A is giving rise to B. And what is the Kc value here? Nothing but concentration of B by concentration of A. He's saying that if you are writing the equation in a new form where B is giving rise to A and E is in equilibrium with A. Now, if we write a Kc dash for this, what it is equal to, nothing but concentration of A product by concentration of reactant, that is B, right? How it is exactly looking? Nothing but 1 by Kc. Whenever we inverse the reaction, nothing but Kc will be inverse of, Kc dash will be inverse of Kc. Just remember this one. Whenever you are reversing the reaction, just write the inverse of the equilibrium constant. That will get you the new equilibrium constant for the reversed reaction. Clear? Whenever you are adding two reactions, multiply the rate constants. Whenever you are reversing the reactions, just inverse the rate constant. Simple. Clear with this concept? If you are clear, let's move to the last small concept, that is equilibrium constant. Third case, if the chemical reactions having equilibrium constant K is multiplied by a factor N, that means we are increasing the number of moles here. Let's say we have a reaction A into A. A is the small a's, small alphabets are the stoichiometric values, into B into B. B moles of capital B is in equilibrium with C moles of capital C plus D moles of capital. Now, here what we are doing, we are giving the moles also. Let's say A, B, C, D are equal to 1 now. Then what is Kc value? Kc is equal to concentration of C by concentration of D by concentration of A into concentration of B. Here small a, small b, small d values are 1. Okay. This is the value. Now let's say I'm multiplying or let's take the values of A, B, C, D as N. That means I'm increasing the number of moles by N times. Then what is the new equilibrium constant? Kc dash will be equal to concentration of C power N into concentration of D power n by concentration of A power n into concentration of B power n. Clear, everyone? Now, if we write it Kc dash simply, nothing but Kc dash is equal to concentration of C into concentration of D by concentration of A into concentration of B whole power n. Simply, we can write as Kc power n, right? Now, what we can conclude from this equation, Kc dash is equal to Kc power n. Equilibrium constant, new equilibrium constant is equal to Kc power n. If you are increasing the value of all the stoichiometric values by n times, the Kc value will also increase by power n times. Power n times. Clear? If you try to note these concepts, tomorrow we'll be doing the problems again based on equilibrium constant values. When what happens when we are adding the reactions, or what happens when we are inversing the reactions. Okay. So if you have any doubts, try to ask. If not, you can leave the chat. Thank you.